There's three basic ways of representing coordinates. Now let's start with the one shown here. In terms of latitude, you could be north of the equator or south of the equator. And the maximum number of degrees is 90 for the North Pole and the South Pole. Now what's shown here is degrees in minutes. There's 60 minutes in a degree. And since the lines of latitude are parallel, the distance between them are constant. There's 1 nautical mile per minute, which is 1.85 kilometers. Now, in terms of longitude, you could either be west of the prime meridian or east of the prime meridian. The prime meridian passes through Greenwich, England. However, the distance between longitudes is not constant because the lines are not parallel. The distance is dependent on the latitude, and it's a cosine function. Now, in terms of the two other representations, you can represent it as degrees, minutes, and seconds. 1 second is 1/60th of a minute. The third representation is just simply a floating point number, where you have degrees and then a decimal value and a positive negative for north, south, east, and west. Now, to get the distance between two coordinates, you can obtain that from simply calling a method on CL location, an instance of it, given another instance of a CL location. I'm going to cover the mathematics behind calculating that distance. Now, you don't need it. However, I think it's valuable to understand the concept. I'm going to derive the formula for the distance between two coordinates with 2 slides of basically high school mathematics. The circumference of a circle is 2 pi r. The radius of the Earth is 6,371 kilometers. Now keep in mind that the Earth is not a perfect sphere, so there's some variation in this calculation versus actual reality, but it's close enough. So the circumference of the Earth is 40,030 kilometers. Now let's think in terms of radians, because it makes the math easier in the long run. 1 degree, there's 2 pi radians in a circle, so 1 degree equals pi divided by 180, which gives a 0.0175 radian number. Now let's take 45 degrees latitude, which is a value of 0.785 radians. So the distance would be the cosine of that value, 2 pi times the radius of the Earth. So if I'm at 45 degree latitude and traveled all around the Earth, I'd travel 28,305 kilometers approximately. Now let's go to the equator. So latitude is 0, and the cosine of 0 is 1. And I only want to go 1 degree along the equator in terms of longitude. So instead of going 2 pi, I'm going 0.0175 times the radius, times 1, which is the cosine of 0. So I'd be going 111 kilometers. Now, 111 kilometers is the equivalent of 1 degree latitude. So the distance at the equator of 1 degree of longitude is the same as the distance of 1 degree latitude. Now, if I take the 111 and divide that by the conversion factor, 1.85, converting kilometers to nautical miles, I end up with 60 nautical miles. Now keep in mind that 1 minute, which is 1 nautical mile, is the equivalent of 1 degree is the equivalent of 60 minutes. So it's 60 nautical miles. Okay, remember, think in terms of radians. Now I'm going to pick some arbitrary variable names. X1 and X2 are the two latitudes. Y1 and Y2 are the two longitudes. Now I want the difference between the two latitudes and the difference between the two longitudes. Now here's where the trick comes in. Distance between latitude is going to vary depending on a function of the cosine. So it's not linear. However, if you take the average between the two latitudes, x1 plus x2 divided by 2, and use the cosine of that as the distance between the longitudes, it's pretty accurate. The result is within a couple hundred kilometers. So effectively what you have is you have a coordinate system of radians. Now, to get that distance, you sum the squares, take the square root. Now, so what you see here is dx squared plus the cosine of mx times dy squared, the square root times the radius of the Earth. Let's take a look at an implementation. Okay, I'm not going to take a lot of time breaking this down. It's an implementation of what you just saw. So you can pause the video and actually analyze it yourself. Question is how accurate is it? And this is a execution of what I just showed you versus the value that is provided by the CL location method. And if you actually do the arithmetic, you'll find that there's not much of a difference percentage-wise. Now, nobody really knows what Apple does internally. Some of this could be the result of a different value for the radius or the circumference of the Earth, or it could be an integration. If you sum smaller portions of the travel, you'd end up with a more accurate number. That's it for now. In the next video, we're going to start looking at application implementation.